Hello everyone, welcome to my YouTube channel. In today's video, we are talking about polymer molecular architecture. Here is a question. You are holding a plastic bag in one hand and a rigid plastic bottle in the other. Both are made from polyethylene, the exact same monomer, ethylene. So why is one floppy and the other so stiff it holds its shape? The answer is chain architecture. The shape of the polymer chain, whether it is straight or covered in branches, changes every single property of the material: stiffness, melting temperature, density, crystallinity, and processability. I'm Mo. I have a PhD in polymer science and I work in R&D in flexible packaging. In this video, the first in a three-part series on polymer molecular structure, we are going to understand exactly how chain topology controls polymer behavior. By the end of this video, you will understand why HDPE is rigid and LDPE is flexible, what a chain extender does, and how engineers deliberately design chain architecture to get the property they need. Molecular architecture is the term we use to describe the connectivity and topology of the polymer chains. How monomer units are joined together and whether those chains are stand-alone or connected to each other. Think of it this way. A polymer chain is like a string of pearls. Architecture describes whether the string is a straight line, whether it has extra pearl string dangling off the sides, whether the strings are tied together at intervals, or whether they form a three-dimensional mesh. Architecture governs chain topology, how chains are arranged relative to each other. It controls chain connectivity. Are they only entangled physically, or are they chemically bound through bridges? And it is why the same monomer can give completely different materials. HDPE and LDPE are both polyethylene. They differ only in architecture. Everything else, density, molecules, melting temperature, application, follows from that single structure differences. There are four main architectural types: linear, branched, cross-linked, and network. These are arranged in order of increasing strength and thermal stability. We will look at the linear and branch in depth today. Here are the four fundamental chain architectures. Every polymer material falls into one of these four categories, or some combination of them. Linear chains are straight, no branches, like HDPE. The chains can pack tightly alongside each other, forming ordered crystal regions: high crystallinity, high density, high stiffness. Branch chains have side chains extending from main backbone, like LDPE. Those branches physically prevent the chain from packing tightly, so lower crystallinity, lower density, much more flexible. Cross-linked. Cross-linked chains are connected by covalent chemical bridges between neighboring chains, like vulcanized rubber. The bridge prevents flow. The material cannot be remelted. Elastic but permanently set. Network polymers are fully three-dimensionally cross-linked. Every chain is part of a single giant molecule, like epoxy or melamine. Maximum strength, maximum rigidity, maximum thermal stability, completely infusible. Direction of increasing strength and thermal stability goes from linear to branch to cross-link and to network. Let us spend some time on linear polymers. They might seem simple, just straight chains, but their properties follow directly from this simplicity in a very elegant way. Because the chain is unbranched, neighboring chains can approach each other very closely. They align in parallel and pack into the ordered arrays. We call this crystalline lamellet. In HDPE, crystallinity can reach 75 to 85%. That is most of the material organized into a crystal lattice. High crystallinity has several direct consequences. First, a higher melting temperature. HDPE melts at 130 to 140 degrees Celsius. You need that temperature before the crystals dissolve and the material flows. Second, higher modulus. Crystals are stiff, and a mostly crystalline material is stiff. HDPE has a tensile modulus of 600 to 1400 megapascals. Third, better barrier properties. In a crystalline material, oxygen and moisture molecules have to navigate around the crystal rather than diffusing freely through amorphous regime. The density follows directly. When chains pack tightly together, there is a little free volume between them. HDPE density is 0.94 to 0.97 grams per cubic centimeter. This is where the H in HDPE comes from, high density, because of tight chain packing. From a processing perspective, linear chains have low melt viscosity as high shear rate. They follow well when pushed hard. This makes them excellent for injection molding, blow molding, and extrusion into thick-walled products. Now branched polymers. The key insight is that branches, even small ones, completely disrupt the ability of chains to pack together. In LDPE, free radical polymerization at high pressure and temperature creates a random distribution of branches, some short 2 to 4 carbons, some long. The process is difficult to control. You get a broad distribution of branch lengths and positions, and this randomness is what makes LDPE so different from HDPE. Those branches stick out sideways from the main chain. When you try to pack two LDPE chains alongside each other, the branches get in the way. They create a steric hindrance, physical interference between neighboring chains. As a result, chains cannot approach each other closely enough to form well-organized crystal lamellet. LDPE crystallinity drops to typically 45 to 55%. Less crystalline means lower melting temperature, 100 to 115 degrees Celsius. Low crystallinity means lower modulus, 100 to 250 megapascals versus 600 to 1400 for HDPE. The material is much more flexible. The density also drops. Loose chain packing creates voids, empty space between chains that is not occupied by anything. LDPE density is 0.91 to 0.94 grams per cubic centimeter. That lower density is directly visible in the feel of the material. It is lighter and softer. But LDPE excels in applications where flexibility is the priority. Its line chain branches give it exceptional melt strength, the ability to stretch and hold its shape during processing before it solidifies. This is why LDPE is the first choice for blow film. The inflated tube of molten plastic that becomes packaging film needs to be stretched without breaking, and LDPE does this brilliantly. Let us put HDPE and LDPE side by side because this comparison perfectly illustrates the entire philosophy of how chain architecture controls properties. HDPE on the left, linear chains, tight packing, higher crystallinity of 75 to 85%, density of 0.94 to 0.97, melting temperature of 130 to 140 degree, modulus of 600 to 1400 megapascal, a stiff, strong, excellent moisture barrier. Its application can be for milk bottles, detergent bottles, water pipes, fuel tanks. Everywhere you need rigidity and chemical resistance. LDPE on the right. Branched chains. Loose packing, crystallinity of 45 to 55%, density of 0.91 to 0.94 gram per centimeter cube, melting temperature of 100 to 115 degrees, modulus of 100 to 250 megapascals. Flexible, excellent film forming, good clarity. Compared to HDPE, applications can be packaging film for bread bags and produce bags, cable insulation, excused bottle, stretch wrap. Notice what changed and what did not. Some chemical composition, carbon and hydrogen only. Some basic chain chemistry. Only the topology changed, and the single change in topology produced two materials that feel, process, and perform completely differently. There is also a middle ground called LLDPE, linear low density polyethylene, a mostly linear backbone with controlled uniform short chain branches introduced by a monomer, by a comonomer, butane, hexane, or octane. The branches are short enough to reduce crystallinity like LDPE, but the backbone is linear enough to give better mechanical properties. LLDPE is the dominant sealant film material in flexible packaging today. Here is something that might surprise you. You can deliberately add branches to a linear polymer after it has been polymerized. This is what chain extenders do. The most relevant example of bioplastic and packaging is PLA, polylactic acid. PLA is a linear, bio-based polymer with excellent clarity and stiffness, but it has a serious processing problems, very low melt viscosity and poor melt strength. When you try to blow it into a film or foam it, the melt just collapses. The chains side pass each other too easily. Fresh linear PLA from polymerization, short chains, low molecular weight, low viscosity, cannot be stable foam cells or bubbles. We added multifunctional epoxy-based chain extender. Commercially, the most common one is Jonquil ADR from BASF. This molecule has many reactive epoxy groups. We blend it with the PLA, melting in the extruder, at very low loading, typically 0.1 to 1 weight%. The hydroxyl groups at the end of the PLA chains react with epoxy groups on the chain extender. One chain extender molecule connects multiple PLA chains. This builds molecular weight rapidly. The result is a branched or star-shaped architecture, multiple PLA arms radiating from a central chain extender molecule. Branched PLA, molecular weight increases dramatically, melt viscosity increases, melt strength increases enough to stabilize foam cell and balloon film bubbles. The same PLA monomer, the same chemical composition, but completely different processability because we have changed the architecture internally. This is just one example of how engineers deliberately engineer architecture to solve a specific processing or performance problem. 5 things I want you to carry out of this video. 1. Linear chains packed tightly into crystals. High crystallinity gives HDPE its density, its stiffness, its barrier performance, its melting temperature. All of it traces back to linear architecture. 2. Branches disrupt packing. Even a small, random branches in LDPE dramatically reduce crystallinity and modulus. The lower density and flexibility of LDPE is a direct consequence of branch-induced disorder. 3. LLDPE is the engineered compromise, a linear backbone with controlled short branches from a comonomer. Better mechanical properties than LDPE while maintaining the flexibility needed for film application, the workhorse of a flexible packaging industry. 4. Architecture can be engineering after polymerization. Chain extender like Concrete convert low molecular weight linear PLA into branched, high melt strength material suitable for foaming and film blowing. 5. Same monomer, different architecture, completely different material. This is the fundamental lesson. Composition tells you what atoms are present. Architecture tells you what the material can do. In video 2, we go deeper into cross-linking, how permanent covalent bridges between chains create rubbers, thermosets, and thermoplastic elastomers. If you found this useful, subscribe and I will see you in the next one. Thank you.